All right, so here we're talking about section 7.7 in the book, and it's about 3D shapes. When we have our typical equation, the sum of the moments equals I alpha, or the angular momentum equals I omega, now it's because omega is a vector, and because h is a vector, we're going to relate them with a matrix expression. And the same thing here, because alpha is a vector and the moments are vectors, we need a matrix to relate these two terms. And you might think like, oh, this is going to be very simple. You just calculate the moment of inertia about each axis. Yes, except that this matrix can have off-diagonal terms for certain interesting cases. And if we were in class, I would ask you, what case, when does that have non-zero terms? Like what kind of shape would have off-diagonal terms? But since I can't wait for you guys to answer it, I'm going to give you an example. So here's an example of a shape that we can rotate it about this axis, and it's going to have off-diagonal terms. And let me explain a little bit why. So first, let's draw a little picture of what we've got going on here. So imagine we have some rotating object here that's going to be rotating about the z-axis. So we'll call this z. And it's going to have mass concentrated in these 2 points, just to make things simple. And we'll call this the j-axis, the y here. And now, what kind of angular momentum is this going to have? Well, you're first thinking, yeah, it's going to have angular momentum in the z direction. And you're right. So here, if we draw this x and y from the top here, we can see that we'd have one of our little point masses would be right here, and the other one would be right here. And this one would have some velocity because we've got this curling in the z direction, so this one would have some velocity. And the velocity of this would be omega times y. If this dimension here is going to be y, we're going to call this one z. So the velocity would be omega times y, and this one would have velocity in this projection here, so we'd have omega times y, and it would also have distance y, so we would have h in the z direction is going to be y squared omega. And then, of course, we'd have 2 of these. All right. So now, but that's not. So that would be like if we were looking at it like this, right? We have some angular momentum in this direction. But we could also look at it in this direction. Now, if you look at it in this direction, it might almost look like I'm rotating it about this axis. Like it might look like there's an axis here, because what you'll see is now if we draw z-axis here and we draw the x-axis out this way, right, where before the x-axis was xy, so x was out here. Now the x is this way, so the y is kind of into the board. And so we've got one ball up here and one ball here. And this ball is kind of like back into the paper, so it is moving this way. And this ball is towards us, so it's moving this way. And the velocity that it's moving with is still going to be omega times y. That's not a subscript, it's a times. Omega y. And this is going to be the opposite direction, omega y. But now the moment is about this point here, because we want to take the moment in the y direction. So we've got this distance in the z. So if we did this, we would have h, a y, and again, there's two of them, and it's going to be in the negative direction. So I'm going to put that negative because if we see this, if we curl our fingers this way, my finger is pointing in the opposite direction of the y-axis, and now we've got y, z, omega. So look, now here we're rotating again, like we're only rotating it about this one axis here, but it's giving us angular momentum about a perpendicular axis, and that's because of the asymmetry. And now in this case, if we did, probably back and we get it in the x direction here, in the x direction we would end up with 0 because there's everything is in that plane, and so we would end up with 0 just like we would expect. So let's think about this generally. How does this normally look? What is the equation for these relationships? Give ourselves some space on my small whiteboard. Draw this out. All right, so what we need is an equation for our matrix I. So let's just give ourselves lots of space. So we're always going to be taking the integral for each of these cases. So I'm going to draw a big integral for all of the mass. We're going to take care of every piece of mass. And here, if this is going to be the component that relates omega in the z with h in the z, just like normal. So that would be x squared plus y squared. And so this is going to give you some radius away from that z-axis. And similarly, you could get some radius from the x-axis with y squared plus z squared, and some radius from the y-axis with x squared plus z squared. And these terms for any, I mean, obviously for a point mass, these might be really small, but for anything that's not a point mass, if it has mass, these terms will be positive and non-zero. Sometimes for something like a thin plate, we might neglect one of these terms, but not the other. And yeah, so you're going to expect these terms to always be positive, always be there. But now, in the other direction, just like we had in that example, each of these is going to be non-zero if it's asymmetric. And what they will look like is they're all going to be negatives. Negative, 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 negative. And it's just going to be whichever component of the matrix you're in. So this is the first row and the second column. So this is going to be x, y. And this is the same. This is going to be x, y. And then here we have x, z. And similarly, here we have x, z. And then here we have y, z. And here we have y, z. So these are the types of matrices we'll be calculating for this section. And these terms are called products of inertia. And they might be 0, especially for a nice symmetric body where you have the same amount of mass on the positive y-axis as on the negative y-axis, and in the positive z and then in the negative z. Then these terms will cancel out when you do this integral. Or they might be negative, or they might be positive. So you need to be careful of your signs. Draw right-handed coordinate systems, like I'm using my left hand, but you should use your right hand. X, Y, these fingers on the Y, this finger on the X, Y, Z, okay? All right, we'll do some examples next.